So in this video we're going to look at our practical results for the Hooke's law. We're going to analyse it and we're going to look at a couple of key terms as well. So starting with elastic deformation, so things like springs and rubber bands. The spring we used in our investigation exhibited elastic deformation, which meant that it returned to its original shape once we stretched it. So if you stretch it and you let go, it will ping back to its original length again. Yeah. In elastic deformation, so things like blue tack and plasticine do this. If you stretch it, it will not return to its original length. It will stay deformed. It will stay in a different shape than it was. Okay, so that's the difference between those two. Now, looking at our results. Now, before we look at our results in detail, I want to recap what extension is. So if you saw our spring, you saw that our spring looked like this. It had a loop at the top, and then the spring itself was all coiled up, and then there was a loop at the bottom. When we added a force to it, when we added that weight, we stretched the spring, yeah? And it became longer. Now, how much longer did it get? Well, that's what our extension is. So if you take the original length, which is here, and you go to the new length, which is here, this change in length here is known as the extension. Okay, so that's the extension. Now, our results show that force and extension are directly proportional to each other. Yeah, how do we know that? Well, there's two ways that we can tell. If you look at the results on the graph, they form a straight line that goes through the origin. That's our first indication that it's directly proportional. Secondly, if you double one of them, so let's double this 2. If you double 2 to get to 4, you will also double extension. So extension doubles to 12.5. It's sort of not exactly doubles, but if in a perfect world it will double. Okay, so it doubles and it goes through the origin, yeah, and it's a straight line, so it's directly proportional. Yeah. Just a little side note as well, I've put force on the y-axis. Normally I'd put the independent variable on the x-axis, but just some of the calculations we're going to do later, it works out better if we've got force on the y-axis. Right, furthermore, if I were to continue adding force to the spring, then eventually it will hit a point here. Okay, at this point it's hit its limit of proportionality, and after which it's hit its limit of proportionality, it will suddenly become very easy to extend. Yeah, it will suddenly flatten, and suddenly it will become very easy to extend. After that point, the spring will no longer return to its original length either. It's now permanently stretched. But we're going to focus on the bits before the limit of proportionality. We're going to focus on all of the bits that we did in the practical. Now, the first calculation I want to do is, well, actually the first thing I want to look at is the directly proportional relationship. So we know that force is directly proportional to extension. This little symbol here means directly proportional to. So force is directly proportional to extension. Now we can rewrite that like this. We can put force is equal to some constant k times by extension. Yeah? Right, let's go over some of these terms. So this is force. This is extension. Force is in newtons, extension in in meters. Okay. Now this k is our spring constant, measured in newtons per meter. Okay. Right. So spring constant then. So the spring constant just refers to how stretchy the spring is. A larger spring constant it will provide a stiffer spring. Okay. So the stiffer the spring, the bigger the spring constant. Now, how can we use our graph to calculate the spring constant? Well, we can do a gradient calculation. We can calculate the gradient of our graph, and that will give us the spring constant. Let me show you why. So the gradient, I'm going to do this by making a big triangle on my graph. Okay, there's my big triangle, and then there's the base of my triangle. Okay, now if I take the height of the triangle, that's my change in y. And I take the base of the triangle, that's my change in x, and I divide the two, I take change in y divided by change in x. That is going to give me change in force divided by change in extension. Force divided by extension is going to give us k, our spring constant. Okay, so let's do that. Let's take the change in y. So y started at 0 and it went all the way up all the way up to 9 on our graph. Okay, so I'm just going to say 9. So that's 9. Our change in x started at 0 and it went all the way up to 30. Okay, so change in y divided by change in x, that's 9 divided by 30. That's going to give me 0.3, and I'm taking a force in newtons and dividing it by extension in centimeters. So in this case it's newtons per centimeter. So that's my spring constant for the spring that we used. We can also calculate the energy stored in the spring. Okay, now the area underneath the graph is going to give me the energy stored by the spring. So this area underneath the graph here. How am I going to calculate the area of this triangle? So it's a triangle. So the area of this triangle is half, because it's a triangle, half times the base, which is given by extension, times the height, which is given by force. Okay, and that's going to give me the energy. Now, we also know that force is equal to KE. So I'm going to replace F with KE. I get half times K times E times by the E again. So I get half KE squared. Okay, so I can actually calculate the energy using this equation here. This is an equation that you will be given in your AQA exam, but you will be expected to be able to use it and know how to use it. So if you want to calculate the energy stored in the spring, you can do that just by taking the spring constant and multiplying it by the extension squared. Okay, and then half it. Right, that's it. That's Hooke's law. That's spring constant. I will see you in the next video.